Okay, so we're going to start 11.9 here, which is on derivation of new power series. And this is going to be derivation of new power series from existing ones. We're going to see a way to do this from scratch in 11.10. That's going to be what's called Taylor series or Taylor polynomials. It's a more general theory, but this is a very essential part of it that relates. We'll see the connection a little bit later on. But for now, the only really existing power series that we know for a given function, so let f of x be 1 over 1 minus x, then we know if the absolute value of x is less than 1, we already know, essentially using the geometric series, that 1 over 1 minus x is equal to x to the n when n starts from 0 to infinity. 1 plus x plus. Okay. So this is what's called a power series expansion of this function, and it works on this particular interval. There is also, like I said, a way to get these from scratch. We'll see that in 11.10. But for now, we're just going to use this fact to derive new series. So the question is how to derive new series. And so there are three ways to do it. One is with substitution. That's what we're going to focus on in this video. In the next video, we'll get into the two other parts, which are by integration and by differentiation. So the reason, one of the main reasons why people like these types of series is that you're allowed to integrate and differentiate on the interval of convergence, at least on the open part of it. And substitution is also can be an effective method in certain situations. So for today, for this video, we're gonna start on the substitution. So let's do some examples for substitution. So let's say we want to find a series expansion for the function, let's call it g of x, which is 1 over 1 plus x. And we'll do that. We'll do one more. Let's say we want to find a series expansion. Find a series expansion for, let's call it h of x, which is 2 over 3 plus 2x. Okay, so let's do these two, and we're going to do it again using this existing series that we already have. Okay, so we already know that 1 over 1 minus x is the summation of x to the n equals 0 to infinity when x is less than 1 in absolute value. Well, if we want to get 1 over 1 plus x, this is 1 over 1 minus x. So what we do is we substitute x with the negative x. All right, so here now, so this is equal to, this is where we're doing the substitution. We're substituting, we're doing 1 minus x here, so we're going to have minus x to the n here. Okay, which is negative 1 to the n, x to the n, and goes from 0 to infinity. And the good thing is also we don't have to do a separate, ratio test to try to check for where this converges. We can simply, and this converges when we can do a substitution here as well, negative x is less than 1. Okay. Well, when is when is negative x in absolute value less than 1? Well, i.e., that's the same as saying simply the absolute value of x is less than 1. So we know then that 1 over 1 plus x is equal to negative 1 to the n, x to the n going from 0 to infinity, and this is true only when the absolute value of x is less than 1. So this is our g of x. This is one example. Let's do another example, which is the h of x. So let's take h of x, which is 2 over 3 plus 2x. So this one's just a bit more involved. We're always going to start off, personally, I always start off with the original series right here. I'm just going to box that in a different color. I like to start off with that because that's what I remember most easily. Well, let's rewrite this. We just basically do a little bit of algebraic manipulation. That's all there is. So this is now 2 over, what I'm going to do is I'm going to factor out this 3. I'm going to write this as 3 times 1 plus 2/3 x. So this is 2/3 times the quantity 1 over 1 plus 2/3 x, which is 2/3 times quantity 1 over 1 minus 2/3 x. And now I say, okay, well, I know that 1 over 1 minus x is the summation of x to the n. So now I use a substitution. This equals, by substitution, 2/3 on the outside. And on the inside, we take the series expansion, and we replace x here with negative 2/3 x. So this is negative 2/3 x to the n, and going 0 to infinity, which is the summation, negative 1 to the n, 2/3. Well, it was going to be 2/3 to the n, but there's this other 2/3 that's lying outside, so I'm going to make this to the n plus 1, and then x to the n. And so now I have a nice series expansion of h of x, and I don't need to do, again, a separate ratio test. You can do that and check that you would get exactly what we're going to get. But this is true when the absolute value of negative 2, because whatever we did the substitution, that's what we substitute in this absolute value sign. Negative 2/3 x is less than 1, i.e. 2/3 x is less than 1 in absolute value, and that's the same as x being less than 3/2 in absolute value. So as long as x is less than 3/2 in absolute value, this thing converges. So let me just rewrite our final product here. So h of x, which is 2 over 3 plus 2x, this is equal to the series negative 1 to the n, 2/3 to the n plus 1, x to the n going from 0 to infinity when the absolute value of x is less than 3/2. Okay, let me leave you here with a little exercise. So find a power series expansion for f of x being 3x over 4 minus 2x. And we'll start with this exercise, and then we'll move to differentiation and integration.